Hello there and welcome to another maths video. Today I'll be doing it on Kruskal's algorithm, which is part of the algorithms on graphs topic of AS Decision 1. We're going to be finding minimum spanning trees using this algorithm. I'll explain what they are. So a minimum spanning tree, sometimes called a minimum connector, is, well, let's look at all the three words in it and we'll see what each one of them tells us about this thing. So it's got tree in it, and a tree is a type of graph which must be connected. So you can't just have two separate graphs. It must be a path from any vertex on this graph to any other vertex on this graph. There must be some sort of route you can take, and also it must have no cycles. So apart from that, if you are on a vertex on the graph and you walk along an edge to another vertex and you keep doing that, there should be no way you can go back to your starting vertex unless you go backwards on an edge you've already travelled on. That basically a cycle, having no cycles means you'd have to do that. So we don't want any cycles in our minimum spanning tree. I'll talk about why in the last point. But the spanning part basically says it includes all the vertices. You can think of these as like towns and cities, and we want them all included. We want basically to be able to get to and from all of these vertices using the edges from any of the other vertices with some of the weights of the graph. Now the last point, the minimum bit, is why we don't include, just keep the graph. We want to get rid and disclude some of the edges already there, and the reason for that is basically we're going to be adding up the weight, the total weight, so the numbers associated with each of the edges that we include, and the more edges we have, the more weight they contribute, and the bigger the total is. And we want to minimize the total. We want to keep it as small as possible. And yeah, so basically we're only going to keep the edges we have to do. So minimize that. So here's my example graph. It's got letters A to G and all the weights are on there. It's not directed. You can go back and forth on either of the edges, and it's not quite completed either. So I'm gonna be going through it on this graph. So step one, put all the edges in ascending order. So I've done that already here. I would not recommend to use the quick sort or the bubble sort algorithm. Do it by inspection unless you're told otherwise, of course, by the question. It's faster to do it by hand, even if it's a big graph. You can get bigger graphs than this, and I'd still tell you it's best to do it by inspection. This is one of the reasons why Kruskal is not a very good minimum spanning tree algorithm. We'll look at prims in the next time. That's a lot better. Anyway, step two, we're going to look at this list, and in turn we're going to evaluate each arc, and essentially we don't include an arc if it forms a cycle. So we're going to basically just look at the graph and look, would including this arc form a cycle with the edges already added? If not, we add it. If so, we don't, we reject it. And essentially, if you've included all the vertices, your job is done, and any other arc would form a cycle anyway, so you don't need to add those in. So going through it, I'm going to get a highlighter in yellow, and let's look at C to E first. So C to E on the graph, that is there. There's two. So of course we can add that because it's the first one. It's not going to form any cycles. Oh, that's messy. A to B is next, so you go in turn. A to B is 4, and yeah, of course, no cycles formed. It's very hard to do that with two edges. F to G, that's 5. We can add that because we haven't actually even connected any vertices with two arcs yet, so no cycles in sight. It's fine to add that in. A to C, that's 6. Notice how A to C and D to G have the same weight. I could have put them in either order. It does not matter when putting them in ascending order. It doesn't matter which one we choose first. They contribute the same weight, so it doesn't mess with our minimum spanning tree. Don't worry about that. It's your choice. So A to C is here, and that has weight 6, and we can add that. Again, look, no cycle is formed because I can't go back to any of these vertices. D to G is next, which is also 6, and D to G is here. That's fine. Again, we basically just need to connect these two like little subgraphs going on here, and we should be all done. And B to D is next with weight 7, and B to D, even though it overlaps with C to E, it's not at a vertex, so it doesn't count. Don't worry about that at all. No cycle has been formed because, but we've completed the minimum spanning tree because we can start at F and go to G to D to B to A to C to E. It may not always be in a straight line like that. It might be branching off, like trees do that, but no cycles, and that's the important thing. In fact, just get my pen here. If I look at C to D here, adding C to D, well, if I had C to D, I could also then go from D to B, from B to A, and from A to C, and we've got a cycle, which is bad. So I don't include C to D, or B to F, or any of these, because now we've finished it. These would all form cycles. So we reject, you say reject C to D, reject B to F. We've done. The minimum spanning tree is the sum of all the weights, which is 2 plus 4 plus 5 plus 6 plus 6 plus 7 plus 7 plus 8 plus 2 plus 4 plus 5 plus 6 plus 6 plus 7. We don't include these. The sum is 30. That is our minimum spanning tree. I hope you enjoyed this video, and yeah, I'll see you next time when looking at Prim's algorithm.